In order to be able to make inferences about a population from a sample, we need to be able to measure the uncertainty associated with the estimate that a sample gives of a characteristic of a population, such as the mean. A well-known example of this uncertainty quantification is a statement of a margin of error associated with poll results. This margin of error gives us what is called a confidence interval around the estimate from a sample that hopefully contains the true value from a population. First, we'll consider the case where the population parameter we wish to know is the mean. We can't find the exact value of a mean without examining every single member of a population, which is impractical. So we try to learn what we can about the population mean from the mean of a relatively small sample of that population. Then, from that sample mean, and whatever knowledge we have about the distribution of sample means for this population, we can construct a confidence interval that, hopefully, can give us some insight into the true value of a population mean. When constructing confidence intervals for the mean, we assume that either the sample size is sufficiently large that we can assume that the sampling distribution of a mean follows a normal distribution, or that the population itself is normally distributed, so that the sampling distribution of a mean is, again, normally distributed. This is because a linear combination of normally distributed random variables, such as the sample mean, also is normally distributed. To construct a confidence interval for a given population parameter, we first need to choose a confidence level, which is usually quite high, that is, at least 90%. This confidence level represents the probability that the confidence interval will contain the true value of this parameter. From this confidence level, we obtain a significance level, which we denote by alpha. The significance level is just 1 minus the confidence level. Now, how do we actually construct a confidence interval for a mean? First, we consider the case where the population standard deviation, sigma, is known. We use sigma and the sample size to obtain the standard error of the mean, which is the standard deviation of a sampling distribution of a mean. Next, we need to find a particular z-score, which we denote by z sub alpha over 2, such that the probability that capital Z, the standard normal variable, is less than or equal to z alpha over 2 equals 1 minus alpha over 2, where alpha is our significance level. The value of z sub alpha over 2 can be found using a standard normal distribution table. Next, we compute the margin of error, which can be thought of as a radius of a confidence interval. This margin of error is capital E equals z alpha over 2 times the standard error of the mean. Then, the interval, with center equal to the sample mean and radius equal to E, is our confidence interval for the mean. Now that we have a procedure for constructing a confidence interval, let's see why it works. The sampling distribution of a mean is related to the standard normal distribution by shifting by mu, the population mean, and scaling by 1 over the standard error of a mean. Also, because the significance level, alpha, is 1 minus the confidence level, we want to construct an interval around x bar such that the probability that the interval does not contain mu is equal to alpha. But this same equation is also saying that the probability that x bar is further away from mu than E is given by alpha. The situation is illustrated here. On the left, we have a sampling distribution of a mean, and on the right, we have a standard normal distribution. The probability that x bar is outside the interval mu minus E, mu plus E, should be alpha, and because of the symmetry of a sampling distribution of a mean around mu, it follows that each of these areas, the left tail and the right tail, should be alpha over 2. Now, we don't know what mu is, but we don't have to, because the sampling distribution of a mean is mapped to the standard normal distribution anyway, and we can compute the z-score, z sub alpha over 2, such that the corresponding left and right tails in this distribution have area equal to alpha over 2. From our earlier characterization of a margin of error, we obtain this probability. But then we can use the symmetry of a normal distribution to focus on a left tail probability, and we can just divide through by the standard error of a mean. But then, on the left side of the inequality, we just get capital Z. And because of a probability on the right side, it follows that this expression must be z sub alpha over 2, which we know how to obtain from a table. We can then conclude that the margin of error for radius over confidence interval must be z times alpha over 2 times the standard error of a mean. Now, let's work through an example. We have a signal transmitted 10 times, but when it is received, there is some error. So we use the received values to obtain a confidence interval that will hopefully contain the transmitted value, which corresponds to the true population mean. The sample size is small, only 10, so we must assume that the population is normally distributed, and suppose that it is known that its variance is 4. We will use this information to construct a 95% confidence interval for the mean. In other words, our significance level is alpha equal to 0.05. We now follow our procedure. The sample mean turns out to be 9.25. Then we get our standard error of a mean from a population standard deviation, which is 2, over the square root of a sample size. Using a normal distribution table, we can find a value z sub alpha over 2, such that the probability that capital Z is greater than z sub alpha over 2 turns out to be alpha over 2. And from a table we get z sub alpha over 2 equal to 1.96. Then we just multiply that by the standard error of a mean to get our margin of error. Finally, we get our confidence interval with center x bar and radius e. Often the goal is to achieve a given margin of error e. We can then obtain the sample size n that will give us this margin of error by rearranging the equation e is equal to sigma times z sub alpha over 2 over the square root of n to solve for n. This gives us the following formula for n. As expected, in order to reduce the margin of error, the sample size must increase.